This lesson is largely review from grade 11 Chem, Unit 1. We're looking at attractions between particles. So if you can think back to grade 9 electricity, what do you remember about opposite charges? Do they attract or repel? Opposite charges attract. Right. Okay, so it's these positively and negatively charged particles or regions of particles that we're going to be looking for in the different attractions between particles. So in part A, you'll see we have an ionic bond. That will occur between ions. So we have a distinctly positive ion attracting with a distinctly negative ion. So full or complete charge on each of those particles, and that is a very strong attraction. In part B, you'll see a diagram that has a positive ion in the middle. Let me just see if I can show you what I'm talking about. So the positive ion is here, and then you'll see water molecules. I've drawn them as V's, so they're bent, and there's a partially positive end at the hydrogen ends of the molecule and a partially negative end up here at the oxygen. And so the green is indicating an attraction between the positive ion and the partially negative end of the water molecule. The fact that the water molecule has a partially negative and partially positive end means that it's a polar molecule, and we call that partial separation of charge a dipole. And so the attraction shown in green is an attraction between the positive ion and the dipole of the polar water molecule. And so we call that an ion-dipole attraction, which occurs, as you can see, between an ion and a polar molecule. Now in section C here, I'm representing just any molecule here. So you'll see that there are positive charges meant to be protons in the nuclei of the atoms that make up this molecule. And then there are negative symbols here representing electrons in that molecule. Here's a second molecule like it, because again, the focus of this lesson is attraction between particles. And so I'm showing with this red line an attraction between the electron in the first molecule and the protons in the second molecule. And that's the same idea. There'll be a positive proton in the first molecule attracting negative electrons in the second molecule. And so it continues between the molecules. So these attractions are called London dispersion forces, and they'll occur between all molecules because all molecules are made of atoms, and all atoms are made of protons and electrons. So what can increase the strength of a London dispersion force? Well, if there are more electrons in a molecule, then the attractions between neighboring molecules will be stronger. So London forces increase as the length of the carbon chain increases. Also surface area. This will relate to comparing boiling points of isomers of alkanes. So you'll see that the surface area changes. So the more stretched out a molecule is as opposed to the more branched or compact it is. So as we see surface area increase, that will also increase the London dispersion forces. In the boiling point video, we'll look at that specifically. In part D, just to recall a dipole-dipole force, that's an attraction between two polar molecules, and that's what I'm showing you here. The partially negative end of one molecule is attracting the partially positive end of a second polar molecule. And so this red attraction is indicating the dipole-dipole force between polar molecules. Now, as polarity increases, so as the molecule becomes more polar, the strength of that dipole-dipole attraction between the polar molecules will also increase. For organic compounds, polarity is introduced into the molecules via oxygen, hydrogen, nitrogen, hydrogen, carbon, oxygen, or carbon, nitrogen, and possibly carbon, chlorine, or carbon, fluorine bonds. So you'll see that I've recorded the electronegativity differences here, which you may recall from grade 11. Electronegativity difference of greater than 1.67 means the bond is ionic, less than 1.67 means the bond is covalent. And so all these bonds here have electronegativity differences less than 1.7, so they're all covalent bonds. When the border is around 0.4, so if the difference is 0.4 or less, then we classify those bonds as nonpolar bonds. The carbon-nitrogen and carbon-chlorine bonds at 0.5 for electronegativity difference are very weakly polar. And then as you can see, the polarity increases until we have the very polar OH bond. So the presence of these electronegative atoms in the different organic molecules will introduce polarity into the molecule. And we'll look at that specifically at the bottom of this lesson. In part E, our last attraction between particles is the hydrogen bond. And so you'll see that I've drawn a water molecule here, HOH, and a second water molecule here, HOH. So the red dotted line here is indicating the hydrogen bond. It is not, I repeat, it is not the oxygen-hydrogen bond within this molecule. A hydrogen bond is an attraction between particles. So the lone pair of electrons on this oxygen attract the hydrogen that is directly bonded to an oxygen in the second adjacent molecule. So again, it is the electronegative atom in one molecule that is attracting to the nucleus of a hydrogen atom that is directly bonded to oxygen, nitrogen, or fluorine. And that's a very strong attraction compared to London forces or dipole-dipole, and so this is referred to as a hydrogen bond. It occurs because this HO bond is very polar. So if this atom is carbon instead of oxygen, this will not be a hydrogen bond. Hydrogen needs to be directly bonded to a very electronegative atom, oxygen, nitrogen, or fluorine, in order for this intermolecular attraction to be considered a hydrogen bond. How can a molecule experience more hydrogen bonding or increased intermolecular forces? Well, it really is due to the number of sites where hydrogen bonding can occur. And so we'll explore that when we go through our different families of molecules. So now that we've reviewed the different types of attractions between particles, we're going to focus in on examples that will be relevant to this unit, so organic examples. I'm asking you here to identify the intermolecular forces that are present in each of the following substances. So I'm referring to a sample of, in part A, a sample of ethane, C2H6, that's a gas, and there are many, many, many C2H6 molecules in a sample of ethane gas. So you're being asked to identify the attractions between neighboring or adjacent particles in a sample of ethane. So in part A, we look at the ethane molecule, and you may need to draw that to recognize what it is. Perhaps you're noticing the formula and thinking about the general formula that follows. It in fact follows CH2N plus 2, so that should be making you think that it's an alkane, or perhaps you sketched it out and realized that that was CH3CH3. Now, as you think about the types of bonds that are involved here, we have carbon-carbon bonds, they're nonpolar, carbon-hydrogen bonds, they're nonpolar, and so an alkane is always a nonpolar molecule. The only intermolecular forces experienced by nonpolar molecules are London dispersion forces. And so the answer to part A is London dispersion forces. So I'm asking you to go through each of these examples and decide and identify the intermolecular forces present. Sometimes there's one, sometimes there's more than one. Check in with the video when you're finished. Okay, so in part B, you may recognize CnH2n and recognize that as an alkene. I didn't draw it, but it really doesn't matter where you put that double bond. You're still looking at carbon-carbon bonds and carbon-hydrogen bonds. And so because there are no polar bonds in this molecule, it is definitely a nonpolar molecule. The only IMF experienced by nonpolar molecules are London dispersion forces. Same thing with benzene. As you check that out, all carbon-carbon and carbon-hydrogen bonds And so because there are no polar bonds here, it is a nonpolar molecule, and therefore London dispersion only. For the 3-chloropentane molecule, we see we now have, in addition to carbon-carbon and carbon-hydrogen bonds, we now have a carbon-chlorine bond. That carbon-chlorine bond, as you saw earlier in the note, is very weakly polar, and so it introduces subtle dipole-dipole attractions. And so this molecule will experience London dispersion forces and dipole-dipole attractions. Okay, in part E, you can see the OH group has been introduced, and it's important to realize that the presence of the oxygen-hydrogen single bond means that that hydrogen is susceptible to a hydrogen bond attraction between the oxygen in one molecule and the hydrogen that is directly bonded to the oxygen in the adjacent molecule. We always have London dispersion forces present, and so this molecule experiences LDF and hydrogen bonding. Okay, jot down these examples and again try to identify the intermolecular forces present and then play the video to see how you did. Moving on. So we know that the structure in F has a carbon double bonded to an oxygen, and so that bond is a polar bond when you check the electronegativity difference. And so there's asymmetry in the bonding here. The C double bond O is pushing electrons towards the oxygen and partially positive at this end. And so between adjacent molecules, that will set up the ability to dipole-dipole attract. And so we'll have London dispersion forces and dipole-dipole attractions. Looking at part G, we have this NH2 group. And so recognizing that that nitrogen is singly bonded to each of those hydrogens, an adjacent molecule would have the same structure, and the lone pair on the nitrogen in one molecule would be able to attract the hydrogen that is directly bonded to the nitrogen in the second molecule. And so we have a hydrogen bond forming right here. And you'll notice that there's a double capacity for that. That could also be occurring at this hydrogen here. And so we have London dispersion forces and hydrogen bonds. Moving on to example H, we have carbon-oxygen bonds right here. Carbon bonded to oxygen, carbon bonded to oxygen. And so because of the shape of the molecule at this point, which you can see in the line structure, it's bent at the oxygen due to these lone pairs repelling the bonded pairs of electrons. That means that there is polarity in this molecule. So we have a partially negative end of the molecule here, and these pieces are partially positive. And so that sets up, as always, London dispersion forces, but in particular, because of the polarity in the molecule, the capacity for dipole-dipole attractions. You'll notice in part I that it's only carbon-carbon and carbon-hydrogen bonds, so there are actually no polar bonds in this molecule at all, so it's definitely a nonpolar molecule, which means London dispersion forces only. J and K are the last two examples, so pause the video and sketch these and try to figure it out, and then check back in. Okay, so we look at J and notice we have this C double bonded to the oxygen, so we definitely have the polar C double bond O. And then we also have this OH piece, and so if we recall, that oxygen is going to be singly bonded to the hydrogen, and because that H is directly bonded to the O, this is now a site where another molecule could form a hydrogen bond. And so we have London dispersion forces, and then we also have hydrogen bonding. Now, this particular functional group or group of atoms is able to hydrogen bond in a couple of different ways. So if I were to draw the structure twice so that you can see the double bond of the oxygen there, as well as oxygen, hydrogen here, and then draw a second structure where the rest of the structure looks like that. You can see that there's actually, well, I'll add the lone pairs of electrons in. There's actually a potential for hydrogen bonding twice, right here between the oxygen on one molecule and the H directly bonded to the oxygen of the molecule on the right, and then also right here. So the fact that we have the double ability for hydrogen bonding is called the dimer effect, and we only see that with this particular functional group. So we have, these are called carboxylic acids, and you'll learn more about them later in the course. Okay, and for example K, it almost looks like the atoms that we had in example J, but instead of having that, we still have the C double bond O, but instead of having that oxygen directly bonded to a hydrogen, there's actually a CH3 group here. And so if I were to redraw this, just to be clear on what we're looking at, you'll notice that we no longer have that OH bond. And so this molecule, although it is polar, is not able to experience hydrogen bonding. There is no hydrogen directly bonded to an oxygen. And so we have the polarity, and so we'll experience dipole-dipole attractions, but not London forces. Okay, so that's it for a review of attractions between particles.